Welcome to the kickoff talk in this room, Developer's Guide to JavaScript and Web Cryptography. This is me, this is Twin Cities Code Camp 14. Here's the abstract for the talk. You maybe saw it in the online guide. It's a big wall of text. So here's one that's a little less abstract. This is what we're going to be talking about today. Stuff to do with the web platform, JavaScript and Web Cryptography. We're going to talk concepts and definitions. Our code samples are going to be using CryptoJS in the browser, and on Node.js, the crypto module on the server. And then we're going to secure the popular TodoMVC application. So that's kind of the main points of the session today. This is me. That's my pretty cloud in the background picture that you'll see. I guess it's only pretty to me. Places I can be found. I work for Thomson Reuters. They sponsored the breakfast. I'm wearing a Thomson Reuters t-shirt. Yay, we're awesome. We'll end the advertisement there. I've worked on a bunch of JavaScript stuff, security stuff, Java stuff, .NET stuff, a bunch of interesting stuff, I guess, but I'm not that interesting. All right, so what do I actually expect from today's talk? So we will, cryptography is kind of a hard, there's some hard concepts in it. So we have a lot of concepts and definitions that we'll go through. Now, there's a lot of slides that have a lot of words on that have these definitions. I won't read those aloud. One of the reasons I tweeted the presentation link ahead of time, so if you want to kind of take a read through that to understand it or be able to back up to it, that's the reason they're there. We'll have some real-world examples. So I've got a lot of attributions and a lot of hyperlinks to stuff. So a lot of this is not me coming up with this stuff. This is stuff that's been out there. I have a lot of JavaScript code samples out there. And like I say, I've forked a lot of them from the internet. So I have a lot of attempts at humor. And those of you that know me know that I will laugh at my own jokes if no one else does. I may actually just stay paused on a slide until everyone laughs. Just imagine what it's like to be my children living at my house. Okay? And then questions at the end, okay, during the presentation. Pretty much anything can go. All right, so these are all the things I'd like to thank. When I was putting this talk together, I was using it as an opportunity to try a bunch of stuff out myself, stuff I hadn't done. I always had this license to WebStorm, had never used it. It actually is really nice. I, of course, had to Google lots of stuff, no secret. The TodoMVC app, I played with AngularJS and CryptoJS, and I built my first Node.js Express app for this presentation. And the last one on the list, though, I'm not so happy with. I thought my Windows Azure deployment went fine, but the live site has actually got 2 bugs I uncovered last night. And I think they're actually bugs with Windows Azure and their IIS Node implementation stuff. So hopefully I can get that fixed, but my local demos work fine. So if anyone's a big Node.js Windows Azure expert, I might ask for some help later today. All right, TodoMVC. How about I get a show of hands for anyone that's kind of looked at TodoMVC in any of the kind of, so good, okay amount of people. So it's I had heard about this project. I had never actually dug into the project. So I thought, you know what, if I'm gonna demo something, it can't look like the demos I usually create. It's got to look good, and TodoMVC look good. Plus, it actually tells a really good story. So TodoMVC is just it's your standard to-do application. You put a bunch of to-do-is, you mark them off. So for today's sessions to-dos, what we're going to do is again review the cryptography concepts that are relevant, and then we're going to use JavaScript and web technologies to go ahead and apply these concepts to this application. And you'll see on the screen, on the to-dos stuff, we're going to secure to-dos with JavaScript cryptography. Okay? So why would we want to do this? Not just for having fun, as part of a code camp talk. But if you look at what TodoMVC does, it stores your to-dos in local storage on your file system. And Chrome keeps that local storage stuff in an SQLite file on the file system. If you look at, here's the locations here for the Mac and for Windows where that's stored. So if you want to look what's in that file, or if you had some malware on your computer looking for what's in your files, you can literally just go to that directory, open it up with an SQLite browser, select star from item table, and look, I can see my to-dos are in there. So imagine these to-dos weren't something silly like securing it, but they were actually something important. Hey, so you might want to have some security there. All right, so in the end, this is what I want. I want to be able to enter a password before I access my to-dos, okay? And I want these to-dos, I want them encrypted at rest in local storage, okay? I want secure to-dos, and I want it to be red, because red means secure. Or maybe it doesn't, but I picked red. All right, arachnophobia means scared of spiders, all right? Okay. Arachnophobia, how about that? Would that mean scared of acronyms? Okay, because there's a lot of acronyms, so if you have this particular phobia, it might not be the talk for you. Okay, my first kind of glossary slide I won't read. A lot of the future definition slides come from this document, which I'm just kind of citing here. A document produced by this group, NIST, FIPS Pub. Again, I won't read through those, but that's the place where these definitions come. So, cryptography is probably the first one I'll read. It's the discipline that embodies the principles, means, and methods, right? Information security, including confidentiality, data integrity, non-repudiation, also a word I have a hard time pronouncing, and authenticity. So, confidentiality, data integrity, they're some of the ones that we'll really be focusing on. These are also probably pretty well known to people. A cipher, that's what transforms something between a plain text and a ciphertext simply. Plain text is usually the data that's input. Usually it's the clear text or stuff you can see. Ciphertext is the output from the cipher, input to the inverse cipher. That's usually the stuff that's scrambled. So, and then a cryptographic key. This is used all over the place. Sometimes it's called a cipher key or a secret key as well. It's a parameter that's used with a whole bunch of different types of cryptographic operations. So it's used in encryption as part of moving plain text and ciphertext back and forth. It's used with digital signatures. It's used with authentication code means. It's a pretty key concept for a lot of cryptography. SSL, I'm sure you've all heard of SSL. Don't really need to talk about that. And yes, I know it's called TLS these days, not SSL. So just like Istanbul, not Constantinople. Okay, I'll just use them interchangeably. Okay, this is the one I was hoping for laughs. Now, I had to look it up, and this was like from 1990, right? So my fear is this is where I know I'm old, because I don't know if everyone you were listening to music in 1990, or if you're still listening to like Sesame Street or Barney or things like that. So, okay, in theory, SSL, I got a browser, or I got a server, I got this HTTPS connection. Look at that. Now in practice, things aren't always that simple. Maybe I have a CDN in the middle, so I've got two separate HTTPS connections. Maybe I've got a load balancer that terminates it. My internal network has got a whole bunch of web servers and app servers and database servers. So SSL is sometimes a little more complicated than just, I got a connection between my browser and the server. So just kind of bringing that up as a point. All right, we want to get to writing some code here. So, is there a web standard for this stuff? Because the first thing I'm going to do is I'm going to look out, see is there a web standard for cryptography. Oh, look, WC3 has got something. Basic cryptographic operations, hashing, signatures, encryption, decryption. Looks pretty good. Okay, check out their charter. Yep, same kind of features I'm looking for: encryption, decryption, hashing, message authentication. Yep, this looks like very promising. When I look at their use cases, cloud storage, data integrity protection, protected document exchange, a lot of the stuff that we would want to secure to do is kind of gets covered with these use cases. This, to me, looks perfect. Does everything I want. It's a web standard. So we check out their charter, and March 2014 expected recommendation. Okay, 2014 isn't going to work for me. What are some other options I have? There is a polyfill for this library, but that's also just under active development. It's mainly meant there to kind of get people used to the API. So probably not what I want to use. So I'll do what every good developer does. I'll go to Google. I'll search for JavaScript cryptography. I'll see what hits at the top of the list. Because if it's not in the first three things, it's probably, why would I want to look at it? So I see a couple good options there. I see a JavaScript crypto library from Stanford. I see a CryptoJS library. And then I see some sort of disappointing news in the middle there about considered harmful. Well, we'll look at that later. Okay. If you look at the Stanford JavaScript cryptographic library, and that's how they cased JavaScript in their stuff. They refer to themselves as secure, powerful, fast, small, and a lot of the work was based on this about 2009 white paper, and they focused on just the K-weight or the size of the file and the performance and getting proper randomness. And you can see from their quotes that I8 was kind of a key browser for them to test things with, and they wanted it small and they wanted a good pseudo-random generator. So it was a good research project. However, you go out to this site and go to their GitHub site. It's not something that's in active development. It was done by some Stanford cryptographic researchers and some of the same people that actually teach the Coursera course, but it's not an active project. It was really meant to be a research project. So it's one option. CryptoJS, the other thing that came up on the Google search. This is one that's out on Google Code. It's got the one main author. He keeps up pretty well on stuff. He already had a SHA-3 implementation in there, and that only kind of was ratified earlier this year. So a lot of good algorithms, implementations. Okay, so that looks pretty good. For the server side, Node.js Crypto, that's kind of the standard. That's the module that's baked into Node. It ends up using OpenSSL under the covers for its implementation, for all the different methods. And then OpenSSL, which is kind of, I guess, considered like a staple of cryptography in the open source community. It's been around for a long time. A lot of things use OpenSSL or bind to the C libraries of OpenSSL. It's commercial grade. It's well looked at. It's an active project, so Node.js uses that. All right, back to this harmful article that we saw as the second search result from Google. This is really an opinion on browser JavaScript cryptography. So, and there are some key points I highlighted here from this article. The author said they're saying if you have SSL, you don't need JavaScript cryptography because you already have real cryptography. Okay. Also, there's no reliable way for this JavaScript code to be verified for execution, because we know that every time you load a web page, the JavaScript files are downloaded, they're parsed, compiled, interpreted, and they're run. And there's no checksums that go down. There's no install and verification. They just pretty much run every time. So it's like every time you go to a web page, you're effectively installing an application. So there's no native way to verify this stuff came from it. Random number generation. You can't outsource that. The JavaScript implementations don't have good random. You can't go to random.org and get random because then you're outsourcing to somewhere else. So they said there's really not any value in using JavaScript cryptography if you already have SSL. So just go ahead, store the key on the server, store the documents on the server, and that's what the opinion of this author was. And I think there's a lot of good points in the article, but my opinion is that they didn't consider that offline user experience, or the same thing that the TodoMVC application does, where it's actually not using a server, it's only using local storage, or it's the offline web app that keeps a copy of stuff local, and you want to secure that. Then I think there is a use case for not just trusting SSL and not just trusting the server. There's another pattern that I ran across from July 2005, so again, a lot of the stuff isn't new, and it was called host-proof hosting, and it's exactly solving the same problem. your data's locked inside of the data cloud and the key's at the browser. So you host your sensitive data, you just keep track of you do your encryption in your browser, you just store it encrypted on the server. So out at the ajaxpatterns.org website. This was kind of another 2011 kind of medical article talking about how they would also do that same kind of host-proof hosting. I'm not going to kind of go through this diagram, but they have the same concept here. The little stick finger guy up on the left, he's entering his passcode, it's generating a key, and that's what's doing all the encryption, decryption in the browser, but the encrypted data is stored on the server. So some of these same concepts are the ones that we will be applying in the secure to-dos app. So if there are requirements for host-proof hosting, they are, yes, you still need to use HTTPS, okay? You still need to trust who's the provider that's hosting your web application and serving your HTML and JavaScript resources, because if somebody injected bad stuff in there, replaced your files, they're going to be able to get at the keys and documents that are secure in your browser, okay? You still need to defend against and accept the risk of some sort of script injection attack where somebody gets other script onto your page that can download. So you still need to handle that case. You can't ignore that. However, storing it secured on the server means any kind of breach of the data center where it's stored only affects the people that are infected during the time. So if your data is secured or encrypted on the server and somebody does inject something bad in, it's only the people that would visit the site while it's infected could actually have their data suspect. So, and then the other kind of requirement that we have today is we want to avoid proving Schneier's law. And if you guys know Bruce Schneier, he's one of these premier cryptographers. He's got this thing that pretty much has been distilled down that anyone can invent a security system that he himself cannot break. So we could make something so complicated that we couldn't understand it, but it doesn't actually mean it's secure. So that's one of the things that we want to do today. All right, we'll go over this quick. I only really care about number A6, the sensitive data exposure. The OWASP top 10 has been updated for 2013. This is the release candidate. The interesting thing there, why I brought it up, was they've actually combined now their insecure cryptographic storage and their insufficient transport layer protection into one rule now. So that kind of covers end-to-end data. That's that second bullet point there. From where it moves from the server to the browser back to the server, they're covering it, kind of covering it all in one rule. And if you think about it, insufficient transport layer protection, the solution to that was just turn on SSL. So it probably didn't deserve its own item in a top 10 list if all it did was say, hey, turn on SSL. So, but this is definitely relevant to what we're doing with this secure to-dos. So I'm not going to read through this one, but I highlighted in blue why we care. It's encrypted everywhere, it's stored long term. And again, local storage, long term. Okay, so we're probably tired of reading slides. We want to try and look at some code. So let's say we pick CryptoJS and we want to download this code and we want to start using it. And we'll see though on the screenshot below that there's this thing called a Sha-1 Checksum when we download this file. And there's some string that starts with 0913, and what that is that's a hash or a fingerprint or a digest of the contents of this file, so you can make sure if you actually get this file and you kind of run the same Sha-1 algorithm on it, that it's actually the same file you want. So if I downloaded this file and I went to the command line, that's the OpenSSL command line thing I would type. I type digest Sha-1 file name, it would kick out that same string. So before we start using that, we'd want to know it's good. Now, like Sha-1 is a cryptographic hash function, and it'll take an arbitrary length string like a whole file and map it down to just a fixed length string. So that's why it was like a whole huge file can turn down into just that hex string we could see on the screen. It's one way, you can't go the other way, I guess, that's kind of obvious. And it's collision resistant. It means that similar files aren't going to produce similar strings. So you can't just go tweak one little bit or one little file in that zip file and be able to make it come up with the same result. All right, we won't read this, right? But this is the definition of Sha-1, because it's not math camp, right? It's code camp. All right, kind of some more examples here, and here's some code. We're all happy, right? Somebody tweet that. We saw before I had the OpenSSL command line for the file, but for kind of simplicity, what we're going to do here is we see the, let's just say I take a string. You know, the quick brown fox jumped over the lazy dog, and I wanted to find what its Sha-1 digest was. I used OpenSSL a lot in preparing this talk because it is such a standard, it's so well known, it's easy to find documentation on. I wanted to make sure that the code that I was writing in JavaScript, the results were correct. I wanted to basically be able to do some test first, make sure am I getting the results I expect to get. So I used a lot of OpenSSL just to find the right answer and then make sure I can actually reproduce that same thing with CryptoJS and with Node.js. So I ran a digest of that string. I get this nice in red 2FD string. And I apologize if any of you are colorblind. I guess red probably wasn't the best color on there, but it helped highlight what was the same on the screen. In CryptoJS, they also have a Sha-1 function. So you take the CryptoJS object, you call .sha1 on it, you pass in the same string, and then you do toString on it and it outputs a hex value. And you can see there, yep, it's the same value. Also with Node.js. You require your crypto module, you create a hash with Sha-1, you call update to pass in the string we want to hash, you run a digest, you say you want it as hex, and again, we get the same value. So, slightly different API signatures between CryptoJS and Node.js, but pretty straightforward. All right, but you know, we're not command line people, right? We're web guys. We're HTML5. We like drag and drop, right? Who likes drag and drop? Or oh wait, maybe who likes tmux? That's what I'll say. Oh, okay. No, we like drag and drop. Sorry. Well, it's just you, Brian. So, what if I want to drag and drop and find out this value? So, we'll see a demo of this in a second, but here's a little drag and drop event handler that goes ahead, it takes the file, runs the, converts the file into a word array, and does a Sha-1 hash on it. So, this is the demo we're going to see. This is going to be the trickiest part of my day, because I'm going to come over here to this, and then I'm going to try and drag a file across screens. That required 2 hands and a thumb and a mouse. There's a reason I'm a software developer and not like a manual labor person.
This is why we use tmux.
All right, there you go. So, look, you can see the Sha-1, the 093 value. Yeah, that's the same value we saw on the previous slide. So I was able to drop the file there, use some HTML5 goodness. Don't try this demo on Internet Explorer. And gave me the file name, gave me the size, did an MD5 and a Sha-1 hash, and kicked out the values I thought. Okay, that's pretty cool. Now I know that file is the file I can use. That seems fair. Down here in the kind of example source code section, you'll see I've got those same code snippets that I had on the slide here. As I mentioned kind of earlier, my demos user are really ugly, so for this presentation I decided I would learn how Twitter Bootstrap worked so I could make my stuff look pretty, make myself look like a web professional. And it actually looked pretty good, I thought. So, although if a bunch of you guys do view source and you look at my app, you'll realize it was a first project for some things. So, I may tweet out for some help later on my demo, cleaning some stuff up. But all right, back to the presentation. So, we now know what a hash is. So, a hash-based method authentication code, or an HMAC. That's something that comes up a lot too. So that uses a cryptographic key, which we talked about earlier, in conjunction with a hash function. Okay? A symmetric key, and that's a key that that kind of does an operation and its inverse. So it's a lot of times, again, a secret key or a cipher key and a symmetric key. A lot of times that those are used interchangeably. So if you know the key, you can kind of go one way and you can come back the inverse way. A digital signature. That's what allows you to take a key and go ahead and sign something. It's kind of like generating a hash, again with an HMAC. You take a hash with a secret, and now you're the only one that can produce that value. So unlike a normal, the SHA-1 hash, which is just easy to reproduce, a digital signature is something that you have to have some sort of secret value or some sort of key to make happen. So where is this kind of stuff used? If you look inside the kind of the Node source code, I guess, there's a Node module called cookie signature, and it's used by Connect, which is used by Express, and it signs the value of a cookie. And you'll see here the kind of the source code below. You'll see that same kind of create, a crypto object, and you'll see create HMAC 256, and it passes in a secret, and then it takes a value and it turns into base 64, and then in the end it replaces some of the characters to be kind of web safe or URL safe. So this function takes a value and it takes a secret and it generates this hash. And what that means is that later on, if I change the value, because I set a cookie up that says isAdmin equals false, and I don't want some hacker just to change it to isAdmin equals true, if the value of the cookie changes, the hash no longer matches in computing, so there you can just reject it. So it's a way for the secret to stay on the server, for you to sign the value of a cookie, and maybe you to do session state that's kind of in the browser but still trusted and secure, as opposed to on the server. So it's a place that signatures are used a lot. So let's kind of explore that from top to bottom. So if I have this Express code, and again, this was my first Node.js, first Express app, so no laughing at my beautiful code. If I use the Express cookie parser and I pass in a secret, and I've called it key here. Now I recommend you don't use key. It's not a very secret since it's been in all the samples. And then I go and I want to create a cookie. And I just want to name this cookie text, and I want to use my favorite string, the quick brown fox jumped over the lazy dog, and I want it to be signed. Node will kick out a set cookie header, and you'll see that the green there is the same text as a quick brown fox. Now it's got $sign or %20s instead of spaces, so it's encoded for that. But the green text is the same, and it kicks out this 97YD blue string there. Okay. So that's what Node generated. So let me, I go into CryptoJS, let me see, can I get the same result? So can I figure out how to do SHA-256 HMACs there? So I can create a CryptoJS.HMAC SHA-56, I can pass in my text, I can pass in my key, I can base 64 kind of stringify this thing, and I had a QUnit test here that checks are those things equal. Yep, looks like they're equal. Now for those of you that are really good at staring at the screen, you'll say, hey Kevin, they're not the same. Look, you have a plus down in the bottom one, but you have a %2b in the upper one. Well, that's just because plus isn't web friendly, so that's one of those things that gets replaced out. So, and then let me just double check the OpenSSL command line, where I learned a lot of command line kung fu here on this for this project. So I echo the string through OpenSSL digest, SHA-256, pass in my HMAC as key, and then I output as binary, and then I go ahead and pipe it back through OpenSSL base 64. And the reason is not all the OpenSSL command lines support all the same flags. So in a lot of them you could either say base 64 or hex or binary, but with digest you could only do binary or hex. So if I wanted base 64, I literally had to turn it to binary and pipe it back through OpenSSL again to get base 64. So, a little tip there. But again, got the same value. Okay, time for second part of the demo. So we'll see some of this in action. Should be a screen like this, and you should see in the hash it should be the same 97Y value. So I'll go over here. Click on that. Now, one of the things we'll notice here is that hashes are fast and actually meant to be fast. So I could type password, or I could type Kevin, or I could type Twin Cities code cap 14, and you'll see that hash just is instantly updated. Hashes are meant to be fast, and they are fast. So we've been talking about SHA-256. You can use almost any hash function with an HMAC. Here's a Sha-1, we saw that before, that's 160 bits. MD5, which is still used for some file integrity, but it's not really, shouldn't be used for cryptography anymore. That's 128 bits. You can see it's pretty.
Hey Kevin, I think
Yes.
we have a question here.
Oh,
Oh yeah, I was just curious about why you used SHA-1 for the hash of the key, the password, but you didn't. But you used 256 for the. Sorry, too early. I lost my train of thought.
oh, you mean that when the file integrity check was SHA-1, or the? Is that what you're saying? That was because that's what the author of that library had published as a hash version of it.
Okay.
So, and then I can flip between hex and base 64. So, I like to click these, they're kind of fun. This is where, when somebody does view source on this and they're actually an AngularJS expert, they're going to tell Kevin, why did you put an on change on every single one of your fields? This is like, that's wrong. There's a better way to do it, so I need to figure out what that is. So, my first AngularJS app as well. It's pretty cool. I like to, but couldn't figure out how to get these things to react without literally putting an on change on every field. So, all right. Anyone want me to type something in here?
Just change one of the letters and see how much the hash changes.
Okay. What do you want
Just
me
as
to?
an example.
Here we'll go to hex. You want me to change the text?
Yeah.
We'll just add an exclamation mark. Or we'll say cat. Or we'll say frog. All right. Now this is the meme that my children are so sick of hearing because I walk around and I say it like 5 times a day. So, but it's true, you can't just encrypt with a password. So there's a lot of times you think, oh, I'll encrypt that with a password. Well, it's not that simple. So I actually had to break out the Lord of the Rings on DVD, and yes, I still only have DVD, so maybe I'll win a big Blu-ray player today. That'd be great. Showed my youngest daughter the whole scene there. Simply walk into mortar. All right, so I need to take a password, and I need to turn it into a key. So cryptographic keys rely on randomness so that they actually are secure and you can't guess them. But passwords are not. Passwords are strings. They're weak, random. They're just not good. So you have to take something that takes a password and it turns into a long cryptographic key. So a key derivation function, or KDF, are these algorithms that allow you to do this. So, and the Pasture-Based key derivation function, or there's a 2 at the end of this, that's kind of the standard way that this is done. So, another pretty slide with pictures. You take a password, you take how long of a key you want, you throw some salt in the mix, you run it through this BBKDF, and you get a key out. And we'll see this in action. Now a salt. That was on the slide. So what's a salt? Well, because you don't want the same password of password always showing up with the same key, you have to figure out some way to mix it up. And that's what a salt gives for you. So it's kind of this mathematical miracle that you can take this thing called a salt, and it doesn't have to be a secret, but it can be random. But it can turn your your randomness into something that people can't guess. So now we can take a little demo of a little Pasture-Based key derivation in action. So we'll go over here. Hey, Soon.
Hi.
Everyone, this is Soon.
Hey.
I tweeted Soon at just before 9 o'clock because I knew he was working at the table. I ordered up some water. Thanks, Soon.
Service here's good.
I work with him on some projects. So now I took him 35 minutes. So it might show up on if I get a little mid-year review feedback form. You know, excellent test plans, great job at managing projects. Takes 35 minutes to deliver me water. All right. So back to the demo. So Pasture-Based key derivation function. So I got a lot of things here. I got, how big a key do I want? 128, 192, 256. How many iterations do I want to run? So how this works is it hash and hash and hash, and just because it's a whole bunch of times on top of each other, just to keep scrambling and get more random data. You start with some sort of passphrase or password. You throw in some salt, and then you get a key. So I'm going to go here with CryptoJS. 100 iterations, which isn't very much. Actually, they recommend now, because hardware is so fast, that you want to be like maybe 32,000 iterations or 64,000 iterations on hardware because it's so fast. We'll see why we're not going to allow that in the demo in a moment. And I'm going to calculate the key. Okay, looks pretty good. Try it a couple times. Let's get the same value. Let's see if our Stanford library gets the same value. Yep, seems like it does. Stanford library is coming in at about 4 milliseconds. CryptoJS library was coming in at 34, 37, 57. And for reference, I have a call to Node.js. Now, you wouldn't want to call down to the server with your secret data. So from a cryptography point of view, this is bad. But from a performance point of view, this is interesting because the Node.js bindings go to the OpenSSL C library, so they're going to be running at native speeds. So I do that, 6, 5, 5, okay. Well, let me crank this up to 1,000, okay? Because if I go more than 1,000, it won't let me, because I put a little min and max value on there. This was to protect myself. I tried more than 1,000, and Chrome said, "Would you like to wait? You have a non-responsive script." Okay, 1,000, Node.js. We'll try it. 8, 10. 11, 12. Okay, so this is not really a lot different there. Stanford, 30, 30, 29, 30. Look at that, that's pretty consistent, it's not bad. CryptoJS, anyone have any guesses?
About a minute.
Not quite that bad.
I think you said
3 seconds.
hashing was fast. Why?
So hashing is fast, but this is hashing 1,000 times over. So a hash, it's kind of a well, and we saw though that the Stanford library at 1,000 still is pretty fast. So the implementation specifics of this CryptoJS hashing, that's not very good. So yes, when we look back at what Stanford said they were going to do, they said they were going to be like focused on performance. Yeah, looks like they definitely were, and it is definitely fast. So what we have, and again, I can generate a different random number, get a different value, different random number, different value. Look at that, it's so exciting. Here's something that's kind of interesting. I'll go to 128, and I'll calculate my key, and you'll see it starts with the same 9D52, okay? I go up to 192, and it just adds on to it. Go up to 256, and adds on to it. So the number of bits you want for keying material just kind of extends out the random data. So it's an interesting property there. And again, this is the same. Probably didn't have this maybe code. I can't remember if this code was there, but here's how it kind of works. In CryptoJS, you take your salt, you pass in a password, you pass in the salt, you pass in the number of iterations, and then you take the key size, which I wanted was 256, but they divide it by their word array object, which is 32 bytes. So an interesting thing here, if I pass the key size in there, it's 256 divided by 32. In the Stanford library, I just pass in 256 for my key size because they assume it's bits, not words. But in the Node.js library, I pass in 256 divided by 8. because they're doing stuff in bytes. So one of the interoperability things as I was figuring out between these different libraries is even though all the APIs take a key size, you know, one of them's taking bits, one of them's taking bytes, one of them's taking like 4-byte words. So that was kind of a key takeaway there. All right. Let's keep going. See how we're doing on time. All right, pseudo-random number generator. Basically an algorithm that makes something random. I won't read through that. Now, random data functions. JavaScript's got math.random, don't use it. Okay? Crossed out. Node.js has got a crypto-random bytes. The proposed WebCryptoAPI has got a get random values. This one is actually implemented in Chrome today, even though the rest of that W3C spec isn't. CryptoJS has got a way to get a random object, and so does the Stanford library. Second thing, and there's kind of some more details in future slides on this, a lot of the data we're getting back is binary data. Well, how do you deal with binary data in JavaScript? You know, you have binary strings. In Node.js, you have things called buffers. In HTML5, in quotes, you got something called a typed array. CryptoJS, they had an object called a word array. And in the Stanford library, they had something known as a bit array. Okay. So if we look at the Node.js crypto-random bytes, okay? Cryptographically strong. This module seems like was added to Node before there was a buffer. Okay? So therefore, even though Node has a buffer, this crypto still uses binary encoded strings. Okay? Now, this is what it says in the documentation, but I don't know if I totally believe it or not, because when I was playing around with it, it did refer to it as like a slow buffer when I was kind of playing with the interactive console. So, being a Node expert, I'm not sure if what that really means or doesn't mean. So, but at least it's documented to be a binary string. So Node.js buffer, they created because, again, JavaScript isn't Unicode. It's Unicode friendly, but it's not nice for binary data. They created this object and they figured a way to convert back and forth. A lot of times what happens is you'll take a string in binary string in JavaScript, you'll just use kind of 1 byte of the character, you'll take that character code and you'll turn it into your binary data. And that's how binary strings work. So, again, like I said, Chrome implements this. It's called get random values on a buffer. Be able to get something back from a typed array. We mentioned typed array before. It's in the traditionally I said there hasn't been binary data. You saw with our drag and drop file implementation that took binary data, that ended up using a type array behind the covers. A lot of the WebGL type stuff uses typed arrays, and that's why this Kronos group, who actually wrote the spec on it, typed arrays work in IE10, except for the uint clamped array, which doesn't. So you can throw errors when you're trying some stuff. So again, don't try my demo in IE, even IE10. So I'll have to figure out how to get some of that stuff working. We mentioned the word array. It's just for a 32-bit object that CryptoJS uses for its implementations. So this is kind of some of the samples off their website. So, all right. This one is funny. I think probably my actually only funny joke, but. So AES, it comes up a lot of the time. It's been around for 10 years. It's kind of like the standard algorithm that everyone seems to go to because it's been around for a while and it's been approved. There are stronger things around, but kind of AES seems like the minimum that when people are doing encryption they use. So I'll let you guys look at that one for a while. Let me know when you've got it figured out. And I love the internet. It's great. You find something like this. And look, this is even Creative Commons licensed. So I didn't even have to steal it. I can just attribute it and use it. Okay, an initialization vector. This is another concept that comes up. This is real similar in concept to a salt. So some sort of starting point to mix up the the cryptographic operation to mix up the encryption, something that makes it so the same data in doesn't make the same data out. So, all right, we're gonna take a little sidestep to understand what the Ssl encryption format is, because OpenSSL did have AES, but we saw that there's this thing called the Initialization Vector, and we've heard of this thing called the SALT. So when you look back at and this is important too for some compatibility reasons. So OpenSSL, you can encrypt something with the password and it dumps something out, and it's got 8 bytes of this salted magic string and then 8 bytes of this salt, and then your encrypted data. And this is something that they did in 2000. So just kind of for some reference here, some more command line kung fu here. If I want to figure out what salted is in hex, there it is. It's that 536 thing in blue. If I go ahead and I encrypt a message, the string message, through OpenSSL, I encrypt it. I do AES-256 CBC. I make password, make my key password. I actually chose for this example so I can get consistent results to pass in a salt. So that capital S is actually the 8 bytes of salt I want to use. Because if you don't pass in the salt is random, and because it's random you can't reproduce your experiments. I chose to pick a salt here, and I dump it out. And you'll see that the 452 number that's in orange comes out as, you can see where it shows up, you can see where salted comes out, and you can see the data that actually comes out is that kind of that pink or fuchsia 23E. Now if I go through, and that's got cut off, but if I just go through and I say, I want to encrypt this without salt, I'll get a different value. I'll get something that starts with 0293. Okay? So I'm encrypting the string message with my string-based password, and these are the different results I might get. Okay. Now, we talked about the password-based key derivation function. Well, OpenSSL had an implementation before that become the standard, so they have their own kind of password to key type function, this EVP. It actually derives a key and an initialization vector from a password and a salt, not compatible with this. So if I run this -p option on OpenSSL, so that same encryption thing I did before, where I just want to figure out, well, what would OpenSSL generate as my salt and key, or my key, what key and IV would OpenSSL generate from this password and salt? These are the values I'll get. So that OCD number in red would be the key that would get output, and that 6C4 in green would be the IV. And we'll be using those in some future slides here. Now, if I actually decide I want to use the IV and the key, the green and the kind of brownish maroon color, and pass those into OpenSSL, yes, I will get the same 23E5 value I saw before. Okay? You'll notice that it doesn't contain the salted and the salted magic string and the salt in front of it like this slide. It just outputs the encrypted data itself, which means that you need to keep track of the key and the IV yourself somewhere. Now, and the IV doesn't have to be secret, so you can store it somewhere, but the key is your secret. If I wanted to reproduce that inside of CryptoJS with the key and an IV, I could do the same thing. You can see the color coding matches the same spot. Here I go ahead and I encrypt. I pass in my key from my test vector, which I colored. I pass in my IV. I go ahead and I encrypt to get my ciphertext, and sure enough, it matches. You'll see though in my test I matched the first, I skipped the first 32 characters there because I wanted to skip over that salted magic string and the salt. But it matched, it really goes, says I want to match the pink value. More code here. I can do the same thing in, if I want to use the salt in CryptoJS, I can use the same thing. Didn't work out of the box. I actually had to write an issue 85 on that. I'm going to fly by some of these. Interestingly, CryptoJS, if you just pass a password in, it uses the no salt option, so it can be OpenSSL compatible, which isn't really that secure because there's no randomness that mixes in. But that's the functionality that, because it's the way OpenSSL works, it's the compatibility they put in. And in Node.js, I can reproduce the same functionality. Get my same test data, I can get my same pink 23E string back out. Now, Node.js on the crypto side, if I just pass in a password on that library as well, it calls down and effectively uses the no salt option of OpenSSL, so I get that same red 029 value. So, even though we learned about password-based key derivation functions, it turns out that some of the libraries in just kind of the simple mode, they don't use that. They use the old, kind of the older style OpenSSL no salt format. So something to watch out. So not all encryption via password is created equal. All right, so let's do a little demo of AES in action. All right, go over here to AES. I've got a key. I've got an IV. In CVC mode, the quick brown fox jumps over the lazy dog. Encrypt it. Looks great. Decrypt it. Shows up. Switch up to Node.js version. Decrypt it. Yep. Encrypt it. Yep, looks good. Decrypt. Yep. Now, we'll flip to hex because it's maybe easier to see. Let's generate a different random initialization vector. And you'll see, you change out the IV, and the ciphertext changes. So, you can watch all my magicness of red text fields. Red, oh, look at that, see? Now it's not red anymore. And it's red, and now it's not red anymore. So remember, you could have multiple bit lengths for AES. You could have 128-bit, you could have 192-bit, or you could have 256-bit. So depending on the length of the key, you get different values.
Is there any reason you use a shorter key over a longer key?
I think there is.
Just to save space?
Maybe, it ends up outputting, because of the block mode, it ends up outputting the same stuff. I think there's computational time. So, maybe you only have that long of a key. I think most things use, I think the way they created AES was so they could allow for different key lengths. And when it was, I think it was like 2001 maybe when it was first come on, don't totally quote me on that, but at that point we didn't have, right now we have AES is baked into Intel chips, so it's basically baked into hardware now. So at that point we didn't have all the same stuff, so. And again here, some of that sample, same sample source code. So, all right. Go back to now, now that we've learned a lot of our concepts, let's get into the kind of the fun stuff. Let's get to our secure to-dos app. So here's what we want to do, right? We want to take our to-dos app. We want to add a password entry field, okay? We want to be able the first time through to be able to set and confirm a password. Subsequent times through, we want to be able to enter that password and validate it. We want to be able to generate an encryption key from that password. We want to encrypt our to-dos, you know, so that they can't be taken. We want to store them encrypted on disk, and then later when we, subsequent times, we want to be able to decrypt those passwords and check for the integrity of the data. So, how this kind of is going to work from a data flow point of view when we get into the OpenSSL is, remember, we've got a salt that we're dealing with, and that's initially random. And the salt is used in conjunction with our password to generate our key. We have an initialization vector, which is also random, and that's used in conjunction with our key and our plain text to get our ciphertext. We also are going to generate an HMAC of the key with the salt, just to be able to like to see that our password is correct. See that it has, so because if we were to enter a wrong password, how do we figure out if the password's wrong? We can try and decrypt the data, and if it doesn't decrypt properly, we'll know it's not wrong, or we can actually do some sort of secure hash function on it to see if it's right. And since a hash is faster, we'll do that. And then in the ciphertext, we actually concatenate the initialization vector, and that's another integrity check, because the IV sits outside of the encrypted value. If we also put it inside, we can compare it. So when we went to the to-do app, first thing I did is I put the word secure in front of it. because that you immediately make something secure. And then I put a password field. It says enter password. So that means when I launch the app, this is what I'm going to see. I'm going to see set password. And then I'm typing my password, and it's going to say confirm password. All right, but when I come in later, I got to type my password in to unlock it. But what if my password's not valid? Well, I need to get some sort of feedback. So we're gonna shake the password field back and forth, and we're gonna make it red. All right. So the password validation code, it turns. Let's see. We want to see the demo. Should we see a demo? Yeah, we should see the demo. We're going to see the demo. So we're going to go here. We're going to enter my password. See if it's right. It's not right. See, do you guys like that? See?
Yeah.
See? I have done this for hours. I've watched this. Because this is like the Mac does this.
Yeah.
But it's hard to get the right wobbling behavior. So I actually got my camcorder out and I videoed it and I slowed it down to see like how many shakes it happens. And I think I have it pretty good. I got a question on Stack Overflow out there.
Is it on GitHub where we can download that same action?
I have a Stack Overflow question with the transition stuff. So isn't that cool? What needs to be done? Well, I needed to have a better demo because I didn't show you the how to like set it the first time. So what needs to be done? Better demo. Okay. Reload it. Hey, no, not good. Test. Oh, now you can see now you know my secret password. All right. Let's go back. So we saw it in action. All right. Password validation. We didn't have I didn't show you where it was set and confirmed. But the first time through, you want to set the password and you want to type the password in the second time so you don't actually type your password in and not know what it is the first time, generate your key, put all your secret to-dos, lose it. So this code works if it's confirm mode, it makes sure they're the same. Otherwise, it adds that shake animation, invalid. How do we generate a key from a password? We use, again, that password-based key derivation function too. We take the salt that we generated, we take the key size we want, we did 100 iterations because we don't want it to take 3 seconds when I type my password in. We turn around here and we see I actually take an HMAC where I take the salt and then I create an HMAC using my key on the salt. So that will actually let me compare it later, so when I type in my password I can again regenerate the same HMAC, and if my password was different, my key would be different, which means my HMAC would be different. Or if somebody went and tampered with the salt, I wouldn't be able to generate the right password anyway because the salt is there. If they tamper with the salt, I would also not be able to generate the same thing. So that would actually let me be able to tell if my password was correct. And then in the red, this function, it calls a function inside the app called decrypt to-dos. And if that fails, decryption failed for some reason. Maybe it's because somebody actually tampered with the encrypted data. So for the purposes of the app, either scenario just shakes it red back and forth, but they are separate things that can be handled. Here's the shake animation. Little WebKit transform, some timings, color. I think on the Stack Overflow question I have the other non-vendor prefixed ones, but worked okay. So salt, shake. So who's got a mnemonic? If you hear both those things, I'm sure you think of this. Salt with the deadly pepper, right? And we'll shake your thing. I could have everyone sing, but then everyone would quit code camp. Jason Bach would be mad. He'd be like, it's the worst attendance ever. We had set record ticket sales. I don't know where everyone went. All right, 1988. That was that one. Okay, just to make you feel old. All right, we already did the demo on that. So some of the changes I had to make for the for the to-do app was when the screen renders, it usually just renders the to-do list, but what I wanted to do was render the password screen until you had entered your password, then render the to-do list. So I had to change up the render function to go ahead and try and, okay, do I have a key already set in the system, then render the to-dos. Otherwise, go ahead and render the password box, and if you were in confirm password mode versus set password mode, well then I'd want to switch the placeholder label and set focus on it and hide the other one. And I did in blue there, I had to change the what was stored from just the to-do array to my new encrypted version of the to-dos. Because what I need to store on disk is not just the to-do string, but also the salt and the initialization vector and the HMAC. So when I actually wanted to encrypt the to-dos, the text in blue is kind of the key things. I wanted to take the salt that I had, turn it into a hex string, and concatenate that with my actual to-do JSON string, and take both of those things and make that the text I wanted to encrypt. Then I took that data, I encrypted it, and then you'll see here the kind of the value that comes out: my salt, my HMAC, my IV, and my ciphertext. So then later, when I'm going to decrypt the to-dos, first thing I will do is I will go ahead and I'll take my encrypted salt, I'll take the key that was generated from my password, and I'll generate the HMAC again. And if the HMAC I generated here, when I turn it into a hex string, doesn't match the one that was on the file system from stored before, well, I know my password didn't match, or my salt was tampered with, so I can just return null from here. Okay, if that part matches, then I'll keep moving on, and I'll set my cipher up, and I'll go ahead and I'll do a decrypt of my data. I'll pass in my initialization vector, which was stored on the file system, my key, which was generated. I'll go ahead and I'll take that data and I'll turn it back into a string, plain text string, and then I will figure out what my string version of my salt was, and then I will. My slide was cut off. I will actually go ahead and see if I can find the salt as the first string in the, we're going back a slide here, where plain text I took hex salt and I added or concatenated this JSON. When this, oops, can't scroll down. When this runs, it makes sure that it finds the initialization vector as the first bytes in there. So, and if it doesn't find it, it maybe knows either the initialization vector was tampered with, or the encrypted data was tampered with, or you could even make that to say, well, the key wasn't right. Because if the key wasn't right, you wouldn't be able to find this data at the beginning, because it would be a well-known piece of data, and but because encryption might take longer than the HMAC was done first. When I actually was writing this to disk, you'll see here, I wanted to take the salt, take the HMAC, take the IV, take the ciphertext, take all four of those things, store them, turn them into an object, JSON stringify it, save it to disk. When it's read from disk, if the first block, if it actually was new or existing, I want to read those things off the disk. I want to parse them back out. If it was the first time through, though, when I first went through and I set a password, there would be nothing on disk already. So at that time is when I have to go ahead and generate the random salt and random IV and return those back. And at this point, there's no HMAC or there's no ciphertext, so I would return null from there. And then if I go back to my file system and I do a select star from item table on Chrome again, I will see my to-dos jQuery encrypted, my salt is there, my HMAC is there, my IV is there, but then my ciphertext is a bunch of scrambled data. So you can't see that you just can't see the plain text or that my to-dos were there. So it is now safe. No one knows what my to-dos were except for you saw me type them in. So nobody else does. All right. So did we do all these things? Yes. We added the password entry field, check, 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 check. Encrypted stuff, stored it, checked the data integrity. All right. 10 minutes left. Got time for some questions. We can go back to the demos. Brian?
Great, so this is one question I have about this that, maybe you answered and I missed it. What I don't quite get about doing this on the client side.
Yep.
Is if the encrypted data is on the client side.
Yep.
And all the things to encrypt, the data are on the client side.
Yep.
And I have the app and all of its source code. What am I actually protecting my data that I'm encrypting against? What's the actual security threat?
Oh, good question. Now, because at this point here, right, because I haven't entered the password yet, okay, and that's only in my head, and it's the word test, so now everyone knows what it is, right? That's something that isn't in the app. So that's not in the source code, that's not on the app. That's something that I'm putting into the system now, and then that generates the key, and then the key is used. So after I enter test, now in memory, the key is there in the JavaScript. So if you actually had cross-site scripting or you had code running on the box you injected in there, yes, you're right, you'd be suspect there. But when you just go to the file system and you look at the local storage, you can't see anything there. So somebody that got a hold of the computer later, or some sort of virus or some sort of thing that's scanning doesn't have access to it. So, and this might be also important in the case of just kind of an app you take offline where you want to do some work on it, but you want to have it encrypted local. A bad thing is if I forgot my password, I'm out of luck. Okay, now I am in luck because it's only 100 iterations and that's easy to crack. And you can see that in the source code pretty easily. So if a real hacker got this app and he said, well, look, you're only doing 100 iterations there, well, that's easy to crack. That's not good. But we saw the crypto, the Stanford library was faster, so hang on. But the bad news there is, yeah, I forget my password, I'm out of luck.
You could just as easily store this on a server and access it from a variety of devices that you might have with you.
Yep. So what that host-proof hosting model said is if you did this same sort of, you enter the password locally, you generate the key locally, that's what that one graphic kind of showed, you could also just store the stuff on the server and access it anywhere. So, but to do MVC just looks so nice compared to the demos that I were writing that looked like the 90s called and they wanted their HTML3 back.
What's the difference between TLS and SSL?
Good. When SSL was in version 3, that was the same as TLS version 1.
Okay.
And then since then, there's something called TLS 1.1 and TLS 1.2, and those are just kind of more enhanced versions of it. The problems you run into is not all browsers really support TLS 1.1 and 1.2. Some do, but it's not turned on by default. Not every server actually supports TLS 1.2 as well. So, but because it's used, TLS is now used so commonly, and I still call it SSL. I didn't want people to flip the bows a bit on me. I think I didn't even know what TLS was. So.
Could you retweet your link because I'm not seeing it on the Twitter stream?
I could. And if you want a non-functioning version of the demo, I had pushed it out to Windows Azure, but I think I found 2 bugs. One, I can't get their Node.js Crypto stuff to work right. I actually get different answers. And 2, I think if you have a file named app.js, it tries to run it on the server and doesn't send it to the browser. So my TodoMVC app doesn't work. So I might try and rename this file later and try and figure this out. But I just discovered this last night about midnight. And when I was demoing doing my run through to make sure I didn't break my demo. And my Windows Azure website version doesn't quite work. But I was hoping to tweet that out so you guys could see how slow stuff was. Alright, let me see. Did I not tweet my thing out here? ECC 14, was it there? Did you click all?
Yeah.
Did anyone see that? Huh? It's there? Maybe hit top or hit all when you're doing a search or something. So, all right. Any other questions? Thank you.
are these conferences where I scale to be tracked. You know, you like, I'll pull up the front of the big